Mr. G here, going to help you with single-step dimensional analysis, and after that we're going to talk about what are called analysis problems. You've just had the basic introduction to dimensional analysis, what dimensional analysis is, what conversion factors are, and how to set up a dimensional analysis problem. What I'm going to show you now is how easy it is to do dimensional analysis, especially when you have your scientific notation math down. The other thing you're going to notice real quickly is that you have to have those metric prefixes memorized. If you haven't done that, you need to go do that. Throughout the rest of the chemistry course, we use the metric prefixes all the time. And so you have to have those memorized. When I say you have them memorized, I mean the symbols, the conversion factors that they are associated with, and what they mean. Okay? So let's get started. The first thing that we want to do when we look at a dimensional analysis problem is we want to ask ourselves, well, what are we converting and what are we converting to? Well, it looks like we're converting from grams, whoops, let me change my color there, can't see yellow very well. We're converting from grams to megagrams. And it's a good idea that once we identify that, to go ahead and write down what that conversion factor is. Since we've memorized the conversion factor for the metric prefix mega between its base unit grams, we should know that there are 10 to the 6th, which is a million, that is a 6, not an 8, 10 to the 6th grams that are equal to 1 megagram. Okay? So we've got that there to the side. It'll be information that we can use. And now the first thing to do to set up a dimensional analysis problem is that we always write out the number we're converting. And that's going to be 2.38 times 10 to the 4th grams. Do not forget to write the unit of measurement. We need that for our problem. And as you remember from our lesson, it's a conversion factor that we're multiplying it by. So we write our multiplication sign and then the line for a fraction, because all dimensional analysis is multiplying by fractions. And it's not just any fraction, it's actually a fraction that has a value of 1, right? Because our conversion factors are really just equalities that have values of 1, right? That's what we learned. Now, since they have values of 1, and we want to make sure that essentially what we're doing is multiplying by 1, we have to make sure our units cancel out. So the next thing we should know is that, hey, grams is what I have here in the numerator. That means grams better be what I have here in the denominator. So I'm going to start off by writing grams there. That means that this is the part of the conversion factor that I write in the denominator. That's what goes down here. So I'm going to write 10 to the 6th here, which means what goes in the numerator? Well, it's this part of my conversion factor. 1 megagram. Right? Now I can cancel things out. I know grams gets canceled out. And then I can simplify my expression like I do in algebra. Well, all this is really turning into is a little algebra problem. So I'm going to make some room down here, and I'm going to say, okay, well, this is really 2.38 times 10 to the 4. I'm multiplying that by 1 here, aren't I? This is just multiplying by 1. So I don't even have to write this anymore, because this number by 1 is just this number. So I'm just going to get rid of the 1. I've got megagrams, which is kind of like an x, right? In algebra, it could be like x or y or z. So but it's not, it's mg. So I'm going to write mg divided by 10 to the 6th. Now this is why scientific notation math is so important, and to understand it is so important, because it makes this so easy. We don't need a calculator to solve this, right? Remember, the rules for scientific notation math when we're doing division are to first do our operation with our front number. Well, our front numbers are 2.38 and, well, there isn't one. That means it's 1. So 2.38 divided by 1 is, well, 2.38. So our answer is going to be 2.38. Then the second step is to do what? Well, we subtract our exponents. 4 minus 6 is what? -2. And that becomes times 10 to the -2. And we're left with megagrams for our unit. There is our answer. See how easy that is when we're doing it with scientific notation math? And then don't need a calculator. Okay? Now, if that one, if you didn't completely get that one, that's fine. Let's do another one. So here we have to convert 1.02 times 10 to the -12th from moles to nanomoles. That's what that NMOL is. Remember we talked about the unit mole? Who cares if you don't understand what a mole is? That we'll get to that in another unit. You just need to know that a mole is a unit, and that when you put N in front of it, that means nano. And you should know what that conversion factor is. All right, so I'm going to start off by saying what I'm converting from is moles, and what I'm converting to is nanomole. And all that means is that in 1 mole, because a mole is bigger than a nanomole, I have 10 to the 9th nanomoles, right? I have to have a lot of nanomoles to fill up 1 mole, since nanomoles are smaller. Okay? All right, well, let's set up our problem just like we did in the last one. We'll start off by writing out the number we're converting, which is 1.02 times 10 to the -12th moles. Always write out your unit. We multiply it by our factor. And again, we say, okay, I'm starting off with moles. I need units to cancel out. That must mean the mole goes down in the denominator. Okay, I look over to my conversion factor and I say, okay, well, mole is here, so that means the 1 must go down here. All right, that means the part that goes on top is this part, 10 to the 9th nanomoles. All right, my problem is set up. I cancel units out, and I condense and simplify. Let's give myself some room over here. So, when I'm simplifying this, I say 1.02 times 10 to the -12th is being multiplied by 10 to the 9 nanomoles. All of that is just being divided by 1, so I don't even have to write that, okay? Let's just forget about it. Now, this is just multiplication scientific notation math, right? Well, the first step in multiplication scientific notation math is to multiply my front numbers. Well, there is no front number here. That just makes it 1. So, just like this one, all I'm doing is writing out this number as my first number. So my answer is going to be 1.02. And then what do I do with my exponents in multiplication scientific notation? Instead of subtract them, I add them. So -12 and 9, right? Well, since I'm already in the negatives, this needs to come up towards 0, right? Up towards 0. Okay? So, what does it become? Well, one step is 11. 2 steps is 10. How many more steps do I got to take? 7 more steps, is that right? So that becomes the negative third. So 10 to the negative third, and we can't forget our unit of measurement, nanomoles. Right? So again, you don't even need a calculator. I mean, you can use a calculator for this part if you have to, negative 12 plus 9, okay? Don't be embarrassed if you have to, use it. But that's like the hardest math you have to do there, okay? If you're doing your scientific notation math properly. So that's how we do single-step dimensional analysis, okay? Make sure you set it up that way every time you follow the steps. Now look, you should not be doing this in your head. You should be writing this out on paper, okay? Use paper and pencil. Show your work. Do it this way every time and you won't get it wrong. If there's a reason why people don't succeed in chemistry, it's probably because they've skipped over this part and they think that they can either do this in their head or they can cheat it out somehow using a different method. All right? I'm telling you, I've been doing this for a long time. I've been doing chemistry for a long time, and I still use this method. So if that tells you something, please just trust me on this. Use this method, because when the problems get a lot harder, you're going to wish you had. All right, let's go to the next slide and let me show you how to do multiple step dimensional analysis. Okay, now that we've done single step dimensional analysis, I'm going to teach you how to do multi-step dimensional analysis. Sometimes we're going to be converting between units where there isn't a single conversion factor that you've memorized, and we need to be able to get there in multiple steps. In this class, we're going to be doing multi-step dimensional analysis a lot later on with other types of conversion factors that aren't just things like milligrams or megagrams. So you really need to know how to do this. We're going to start with these simple units of measurement, and it's important that you get this under your belt now. So let's see what this looks like. It's not much different than the steps I taught you before. We're just adding another conversion factor into the mix. So the process is very similar, almost identical. What we do is we look at our problem and we say, okay, where are we starting? Looks like we're starting in number 1 from megagrams, excuse me, not megagrams, little m, milligrams. And where are we going? To megagrams again. Now, what we want to notice is that milligrams to megagrams, we didn't memorize one single conversion factor. So in order for us to get from milli to mega, what we want to do is we want to first go to grams, because that's the conversion factor we know, right? We know milligrams to grams, and then we know grams to megagrams. We know that there are 10 to the third milligrams equal to 1 gram. And we know that 1 gram doesn't work out that way, does it? And then we know there are 10 to the 6 grams equal to 1 megagram. Split that up so we don't get it confused, right? So these are our 2 conversion factors. Okay? Both of them will together get us to where we need to go. 2 conversion factors act as like a bridge between the two different units of measurement that we need. So to get us between milligrams and megagrams, the bridge is our base unit grams. So we need to use the two conversion factors to get there. All right, so setting up the problem is very similar. We always start with the number we're given. All right, so we're given 1.02 times 10 to the negative 2 milligrams, so we write that out. We do the same thing we did before. We write a fraction. And same thing we did before. We say, okay, milligrams is here. That must go down in the denominator. We find in our conversion factor where milligrams is, and we say, oh, 10 to the third must go down with it. And for that conversion factor, what goes on the top? Well, 1 gram is equal to it. Now, this is where it's a little different, but it's still very similar. We cancel out what we have, right? And then we pick up where we left off, and we say, okay, well, what's on the top now? Grams is on the top now. We still need to multiply by our second conversion factor. So we write another multiplication sign, and we say, okay, well, since grams is on the top, grams must be on the bottom so that that can too cancel out. I know that 10 to the 6th goes with grams here, so that must go on the bottom. And finally, that means 1 megagram must go on top. You know that you set this up properly if in the end, what you're left with is the unit of measurement that you're trying to convert to. And we are indeed trying to convert to megagrams, and megagrams is indeed in the numerator at the end of our problem. So, what do we do now? Well, we simplify, just like we did before. So let's move it down here and simplify it. 1.02 times 10 to the negative 2. All that's getting multiplied by 1. We can just leave the 1's out and leave ourselves with megagrams. Divided by, it looks like I have a 10 to the 3 I need to write here, which is being multiplied by 10 to the 6. So 10 to the 3 times 10 to the 6th. Now remember, if we use scientific notation math, this process becomes fairly easy. So if we do order of operations, we can make this even easier on ourselves. So let's start by simplifying the denominator. We're doing multiplication math with scientific notation. The front numbers are both 1, so we can ignore that, and all we really need to do is add up our exponents, because this is multiplication. So what's 3 plus 6? Well, that's 9. So let's simplify this even further over here to the left. We have 1.02 times 10 to the negative 2 megagrams over 10 to the 9. Now, if we simplify it all the way down to our final answer, remember this is division with scientific notation. We divide the front number by 1. We end up with 1.02. Division scientific notation math tells us to subtract our exponents. So negative 2 minus 9 is negative 11 times 10 to the negative 11 megagrams. And there is your final answer. So you can see that multi-step dimensional analysis is not much different. The key is remembering that we need to have multiple conversion factors to get from where we're starting to where we need to go. And that, of course, relies on you making sure you know your metric prefixes, as we've said before. And the base unit is our bridge to get from where we are to where we need to go. So let's practice one more together. Here, we're converting from 3.7 times 10 to the 10 picometers all the way to, what is DAM? It's not like a beaver dam. That is decameters. So, it's always a good habit to write from where we're starting to where we're going. From picometers to decameters. Now, what's our bridge? Remember, if we're at meters is our base unit, so that's our bridge. So we have something that's small. That means that there are going to be a lot of what's small in one thing of the base unit. So 1 meter should be equal to, do you remember what pico is? Well, that's going to be 10 to the 12th picometers. 1 meter equals 10 to the 12th picometers. Now, decameter, that is not a decimeter, that is deca, so that's bigger, okay? Now, that is going to be, that's going to mean that there's many of the meters in 1 unit of the decameter, so we'll write 1 DAM. How many is the question? How many meters? Well, it's 10 to the 1. There's 10 of them. Okay? So 10 to the 1 meters equals 1 decameter. All right, so now that we have our conversion factors, it's as simple as setting it up properly and simplifying and doing our math. So let's do it. How are we going to do it? We're going to start off by writing 3.7 times 10 to the 10 picometers. Remember, we're going to multiply that by our first conversion factor. Remember, this is what we're starting with, so what must go in the denominator? Picometers. So we write it. We then say, okay, picometers, here's our first conversion factor. That must mean 10 to the 12 is what I write alongside of it. Now, to finish off that conversion factor, we find out what it's equal to. That is 1 meter. And then we cancel that part of the problem. Cancel out picometers. Now, our goal was not to convert to meters. We need to go all the way to decameters. So, we finish off with our second conversion factor. We say, okay, meters is here. That must mean that meters goes in the denominator so that they cancel out. Then, we go to our second conversion factor and we find meters and we see what's next to it, 10 to the 1. 10 to the 1 must be in the denominator. I say, okay, I must finish the numerator. That means 1 decameter must be what goes on the top. I then cancel out. I ask myself, is what I'm converting to decameters in the numerator of my setup at the end? It is. I've set this up properly. Now I can simplify. All right, so let's condense this here over to the right. 3.7 times 10 to the 10 DAM over 10 to the 12 times 10 to the 1. Order of operations, let's get our denominator simplified first. 10 to the 12 and 10 to the 1 multiplied by each other. Remember, we can add the exponents to simplify. 12 plus 1 is 10 to the 13. So I'm just going to cross this out and say 10 to the 13. Now, if we simplify it even further with division in scientific notation, we remember that the first step is to divide the front number, which is 3.7, and then subtract our exponents. 10 minus 13 gives us what exponent? 10 to the negative 3 decameters. That is our final answer. No calculator needed. You should feel very accomplished after doing these problems, especially without calculators. You are well on your way to becoming an amazing scientist and chemistry student. Give yourself a pat on the back. Take a break before you do some practice on your own.